Okay, continuing on with the 2024 free response questions from the AB Calc exam, we have FRQ number 4 on the BC exam, which is also, I believe, the fourth question on the AB exam. So we're given a graph, and this is the graph for some differentiable function f that is defined on the closed interval from -6 to 7. We're told that it has a horizontal tangent line on x is equal to -2, and this portion of the graph right over here is actually linear from -2, excuse me, so from linear from 0 to 7, I apologize, from 0 to 7, there it is. All right, and we're also given a shaded region R, which is bound in the second quadrant of this graph, and the vertical line x is equal to -6, the x and y axes. All right, and they actually give us the area of this region here, so we'll just write that in. The area of this region is 12. All right, so this problem has a couple different parts, so let's go through it part by part. So I'm just going to kind of move down here so we can see this first one. All right, so for part A, it's asking us to work with this function g that is defined as being the definite integral of this function, f of t, from 0 to x. And it's asking us to find three values evaluate this function g at three different values. So I'm actually going to move in a slightly different order. I'm going to start with g of 4 first, because you'll see in a bit that we actually can use g of 4 to find g of 6. So let's start with g of 4 first. So g of 4, we can then say, since g of 4 is the definite integral of this function from 0, since we're evaluating this at 4, 4 is going to be our upper bound, f of t dt. All right? So this is g of 4. So if we look at the function, what is the definite integral of this function f from 0 to 4? Another way of thinking about this is, what is the area that is enclosed in this region between the x and y axes, and underneath this curve? Well, you'll see here that we really just have, I'll just kind of lightly shade this in, we just have this triangle here. And so we can write this as 1/2 using the formula that we know for the area of a triangle. 1/2, the base is 4, right? The base here is 4. The height is 2. So 1/2 base times height, and that just gives us 4. 4 units squared, and you can just write 4 for now. Okay? Now, what about the g now evaluated at 6? So for now, we're evaluating this integral from 0 to 6. We're extending this all the way over here. We also want to consider this region down here as well now. Okay? And since this region is below the x-axis, this is going to be a negative area, right? So g of 6 now is going to be what we found for g of 4 previously. Now, minus this purple region right here, which again, we're going to go 1/2. The base is 2. The height is 1. And if you wanted to do this where we're adding this area and using -1 for our height, we could have done that as well. But just doing it this way, we're going to get 1/2. Oh, well, let's actually write in what 4 is. G of 4 is. So 4 minus this entire region here, which is just 1, and that gives us 3. Okay, and let's actually make this area, or make this a little bit smaller. Okay, actually, we have enough space to work with. I think we can do it. All right, so now let's do g of 6, and I'll just, g of -6, excuse me. I'll do this right underneath. So g of -6, so let's think about this for a second. G of -6, well, this is the definite integral from 0 to -6 of f of t. Okay, now since our integral is defined, g of x is defined as the integral of this function from 0 to some value x. If we're going to -6, we're actually integrating right to left. And if you remember, integrating from right to left then is equivalent to actually integrating this from -6 to 0 and flipping the sign, or the opposite of this definite integral, if you will. Okay, so the area from 0 to 6 is the equivalent to the opposite of the area from -6 to 0. And there's no work that we need to show. That's given to us. This is just going to be -12. Remember, in the problem, we were told that this region here underneath the curve is going to be +12, so the opposite is just -12. All right, moving on to part B. Part B, so now we're given, we're again working with function g, but it says for this function, find all the values of x in the interval from 0 to 6 at which g has a critical point. And then we're going to need to provide some justification, a reason for our answer. So, all right, so let's think again about what it means for there to be a critical point. And I'll work with a different color here so we don't get mixed up with part A. So in order for it to be a critical point, that's all the places where our function may have a derivative value that is either undefined or 0. So I'm actually going to write it like this. I'm going to say that g prime of x, the derivative of g, is equivalent to f of x, right? If g is the integral of f of x, then g prime of x is just simply f of x. So we're looking for any place where f of x is either equal to 0 or undefined, right? And we can see that f of x is defined for across over our entire interval from 0 to 6. So there's no place where it's undefined. But we do see that f of x is equal to 0 on our interval 0 to 6 when, and ask yourself, do I see it? Yeah, when x is equal to 4. So this is our only critical value. This is the only critical value we see. This is the only value for which x, or I will just say our only critical number or only critical point. This is the only value for which f of x is equal to 0, since there's never a place where it's undefined on 0 to 6. Okay? And that's pretty much all we needed, right, for that part. And finally, for part C, now we're dealing with another function, h, and this time we're told that h of x is defined as the function from -6 to x. So that's great. So we don't have to worry about possibly having to integrate from right to left. So with this function h, again, it's asking us to evaluate a couple of different values, h of 6, h prime of 6, and h double prime of 6. So let's go through it part by part. And I'll just switch to a different color just for consistency's sake. All right, so h of 6 is going to be the integral from -6 to +6 of this function f prime of t d of t. And there's really no work that you need to show here, right? So we can say, well, actually we can show some work. We can say that our function, this is going to be h of 6, or f of 6, I should say, minus f of -6. And so we're just looking at values here. We're saying f of 6 is going to be what? -1. So I'm going to write -1. Minus what's f of -6? And be careful here, before you jump in straight to say that's 1, we actually see that it's 0.5. So we're going to say minus 1/2, and that's going to give us -3/2. Okay? And then h prime of 6, well, what is h prime of x? H prime of x is just going to be f prime of x. Okay? And so h prime of 6 is f prime of 6, which then would be equal to -1/2. Why is it -1/2? Well, again, since we're dealing with the derivative, what is the slope at 6? Kind of look at this slope right over here. It appears to be -1 over +2. So -1 over +2. So we can see that there. All right, so that's h prime of 6. And finally, let's look at h double prime of x this time. So h double prime of x has got to be f double prime of x. So h double prime of 6 is the same thing as f double prime of 6. And what is f double prime of 6? Well, we're looking at this function here. We can say, well, because h prime is constant on our closed interval from 0 to 7, so the derivative of a constant has got to be what? It's got to be equal to 0. Okay, so this work would work well, but we can write that because h prime is constant on our interval from 0 to 7, right? We're saying that this is constant, right? So the derivative of a constant is always 0. Okay, and there we go. Those are the solutions to the fourth FRQ from the 2024 calculus exam.